In this video, we're going to talk about symmetry. And so there's two kinds of symmetry that we're really concerned with in geometry. We're concerned with reflectional symmetry, which is when you can fold a figure onto itself. And we're concerned with rotational symmetry, which is when you can spin a figure and make it land back on itself. So we're going to look at both of those really quick. Reflectional symmetry, like for instance this rectangle, has one line of reflectional symmetry that goes down the middle here. Because if I folded this rectangle over this line, this half would land on this half. It also has reflectional symmetry going the other direction. If I can get my arrow to move up there. Like this. It's not a very straight line, but you get the idea. That if I were to fold the rectangle in half this way, it would reflect over this line. The arrow over here only has one line of reflectional symmetry, and it's the line that goes straight through the middle like that. This diamond would have two. It would have one going straight up and down, and then the other one going straight across like this. The pentagon right here actually would have five. It would have one line going through here, just like that. And then if I turned it the correct number of degrees, it would actually have one going through each one of these vertices. Didn't do a very good job on that. That's a little bit better. So it would actually have five, one going through each vertice, kind of like that. And then this parallelogram right here actually doesn't have any, because if I were to fold it this way, this point that's sticking out would be sticking out over here, not down here. And if I were to fold it the other way, going flat, it'd be the same sort of issue. This point that's sticking out here would be down here sticking out. So the parallelogram actually doesn't have any reflectional symmetry. All right, for rotational symmetry, that's where you can spin a figure and it lands right back where it started. So obviously this rectangle has rotational symmetry. I was able to spin it halfway around, make it land upside down back in the same spot. And then I could spin it one more time. Rotational symmetry is talked about in terms of its order. And an order is how many times you can spin a figure before it comes back to where it started. So for instance, this rectangle, I could spin it once and get it to land back in spot. And then I could spin it twice and it goes back to where it started. Right? This arrow, if I spin it like this, it's not back how it started. So the arrow actually does not have rotational symmetry, because whenever I rotate it, it doesn't land back on top of itself until I rotate it all the way around 360 degrees. This diamond here, you can't rotate it like this, but you can rotate it 180 degrees, so that's one, and then 180 degrees again, so that's two. So this would have an order of two. This does not have rotational symmetry. This one has an order of two. Let's talk about the parallelogram really quick. It's the same sort of deal. Oops, there's one, and there's two. So the parallelogram also has an order of two. The pentagon, again, is interesting. I didn't do a super good job of making this pentagon to make it as regular as I wanted it to be. But a pentagon actually has an order of five, because I can spin it once, twice, three times, four times, five times before it lands right back on top of itself. And now, like I said, whenever I spin this, it winds up getting off just a little bit. That's because I didn't do a very good job of centering my pentagon. But the idea still stands that you could rotate a regular pentagon 5 times, one time through each vertex before it lands back on top of itself. So a regular pentagon has rotational symmetry of order 5.